At the beginning of the 20th century, our understanding of the universe changed forever. For centuries, scientists believed that space and time were fixed and absolute. Time moved forward at the same speed for everyone, everywhere. Space was simply the stage where the events of the universe happened. But in 1905, a young physicist named Albert Einstein proposed an idea that would challenge this view completely. He suggested that time and space are not separate things. Instead, they are deeply connected, forming something we now call space-time. To understand this idea, imagine that space and time are woven together like threads in a fabric. Everything in the universe, planets, stars, light, and even you, moves within this fabric. But here's where things become surprising. According to Einstein's theory of relativity, time does not move at the same speed for everyone. It depends on two things, speed and gravity. Let's start with speed. One of the central ideas in Einstein's theory is that the speed of light is constant. No matter who measures it or how fast they are moving, light always travels at the same speed, about 300,000 kilometers per second. Because this speed cannot change, something else must adjust when objects move very fast. That something else is time itself. When an object moves close to the speed of light, time for that object begins to slow down compared to someone who is standing still. This effect is called time dilation. It sounds strange, but it has been confirmed by experiments many times. For example, extremely precise clocks placed on fast-moving airplanes tick slightly slower than clocks on the ground. The difference is tiny, but measurable. Now imagine this effect at much higher speeds. If astronauts could travel close to the speed of light and return to Earth, they would find that less time had passed for them than for the people who stayed behind. In a sense, they would have traveled into the future. The second part of Einstein's theory involves gravity. Before Einstein, gravity was thought of as a force that pulled objects together. But Einstein described it differently. According to general relativity, massive objects like planets and stars actually bend the fabric of space-time. Imagine placing a heavy ball on a stretched rubber sheet. The sheet curves around the ball. If you roll a smaller ball nearby, it will move toward the larger one, not because it is pulled directly, but because the surface itself is curved. Einstein proposed that gravity works in a similar way. The Earth does not simply pull the moon with an invisible force. Instead, the Earth bends space-time, and the moon follows the curved path created by that bending. Even light is affected by this curvature. When light passes near a massive object like the sun, its path bends slightly. This prediction was confirmed during a solar eclipse in 1919, providing one of the first major confirmations of Einstein's theory. Gravity also affects time. The stronger the gravitational field, the slower time passes. For massive objects like black holes, this effect becomes extreme. Time near the black hole moves much more slowly than time acceleration. As to observe a watching from a distance, someone approaching a black hole will move slowly. These ideas may sound abstract, but they are not just theoretical. Modern technology relies on them. For example, GPS satellites orbit the Earth at high speeds and experience slightly weaker gravity than we do on the surface. Because of this, time on those satellites runs at a different rate. If scientists did not correct for these relativistic effects, GPS systems would quickly become inaccurate. So the device you use to navigate your city works correctly because Einstein's equations describe the universe accurately. Relativity teaches us something profound about reality. The universe is not as simple as our everyday intuition suggests. Space is flexible. Time is not universal. Motion and gravity shape the structure of the cosmos itself. What once seemed fixed is actually dynamic. Einstein's ideas did not make the universe more chaotic. They made it deeper. They revealed that the laws of nature are subtle, elegant, and sometimes surprising. And perhaps the most remarkable part is this: the same principles that govern the movement of distant galaxies also shape the way time flows around us here on Earth. The universe is not only vast, it is interconnected in ways we are still learning to understand. And Einstein's theory of relativity gave us the first glimpse into that extraordinary structure.